Hello and welcome to another episode of Research Talk. Today we have with us Mr. Deepak Kushwaha from Ghazipur, Uttar Pradesh. Deepak completed his BSc from Banaras Hindu University and MSc from University of Hyderabad. And he is currently working as a research scholar at the Indian Institute of Science, Bangalore. His research focuses on developing a new glycosylation methods for oligosaccharide synthesis in carbohydrate chemistry. Today, he'll be sharing his work on shelf-stable 3-thiocresylpropanonyl TCP glycosides in oligosaccharide synthesis. So, Deepak, welcome to the talk and the screen is yours.
So thank you, Mahesh, for your kind introduction. So today I'll share our recent efforts toward improving the reliability and scalability of glycosylation reactions centered on the new class of shelf-stable donor, that is 3-thiocresylpropanonyl TCP glycosyl donors. So before coming to our main talk, which is main work in which it is based on the glycosylation in this new glycosyl donor has been coupled with various acceptors to form the oligosaccharides or disaccharides. So before coming to our main talk, I will briefly talk about glycosylation. So glycosylation is the process in which glycosyl donor, which contains the leaving group, and glycosyl acceptor, which contains the free hydroxyl group, is coupled in the presence of some promoter to form the new linkage, that is glycosidic linkage. So this bond is known as glycosidic bond. So if we'll talk about the general mechanism of glycosylation, so in that glycosyl donor, in most of the time it is some sugar moiety, either it will be pyranose, furanose, septanose or something. In that anomeric carbon which will be attached with some protecting group, first it will be transformed to the leaving group which is known as the glycosyl donor, and then this leaving group, in the presence of some promoter, it can be transformed to some activated species. Ultimately it will lead to the formation of glycosyl oxycarbenium ion, and then this oxycarbenium ion, it can be coupled with the various glycosyl or aglycosyl acceptors, lead to formation of the glycoside, and the newly formed bond is known as glycosidic bond. So if we'll talk about the some general glycosyl donor, so these are the some most utilized glycosyl donor, starting from the glycosyl bromide, which is developed by Koenigsegg in 1901, and then glycosyl fluoride developed by Mukayama in 1981, then thioglycosides, which is developed by Per Garrick, then sulfoxide donor developed by Daniel Kahn, and then trichloroestamidate donor, which is developed by Richard R. Schmidt. So all the donors are activated from the atom present which is next to the anomeric carbon, or maybe second next to the anomeric carbon. The other than this, there is another class of glycosyl donor which can be activated from the remote position. Like if we'll take this pentenyl glycoside, which is developed by Fraser Reed in 1988, it can be activated from the remote activation. In this case, the uh, site of activation is located remotely from the site of reactivity, which is anomeric position. So other than this, there is another donor developed by K. Scheme in 2001. This is also activated remotely using triflic anhydride. Triflic anhydride lead to the formation of corresponding glycosides. And then in 2006, Professor Hota group has developed this alkynyl glycoside, which can be activated in the presence of gold 3 catalyst, again from the remote position. And in 2008, Bayu group has developed this donor, which can be again activated using gold 1 catalyst from the remote position. And then in 2016, Quen Vance group has developed this sulfide donor, and again it can be activated from the remote position. And same time, this KS Kim and Quen Vance donor can be used in latent active for fashion also. In this donor is the latent form of that glycosyl donor, and this is the active form which can be activated in the presence of promoter to form the various glycosides. So why this strategy is important? So because remote activations offer a powerful way to decouple the site of activation, which is anomeric position, from the site of reactivity. By using the temporary tether or remote tag, it becomes possible to exert better temporal and spatial control over glycosylation reactions. And that's how this strategy opens a new door for selective activation in one pot and iterative setting. However, its implementation is often limited by the donor stability and the need for highly specialized activation method, which we are seeing here. But the key system that has helped to bridge this gap is the allyl glycoside. So what is the advantage with allyl glycoside? It doesn't require the installation of any alternate leaving group. The same allyl group can be used in as a protecting group or also glycosyl donor wherever required. So if you see few example, first example based on the allyl glycoside comes from the Professor G.J. Bones group in 1994, where they have used this substituted allyl glycoside. First, they have used this rhodium catalyst to transform into the vinyl ether moiety, that is the active form of this glycosyl donor, which again it can be uh, activated in the presence of TMSOTF as an promoter and acetonitrile as an solvent at minus 25 degrees Celsius, and it was coupled with the latent form of acceptor to give the desired glycoside, and this new glycosidic bond has been established. And moving further from this, Professor Wang group has developed this allyl glycoside, and they have used iridium cord catalyst to transform to the vinyl ether moiety again, and it was coupled with the acceptor in the presence of NIS as a promoter. So in all these cases, the metal catalyst has been utilized to transform the allyl glycoside to the corresponding vinyl moiety, which is the active form of glycosyl donor. But in 2018, Professor Jayaraman group has utilized the allylic bromination condition, which is different from the metal catalyst. So as it is very well documented in the literature that allylic bromination will selectively brominate the allylic carbon in the presence of NBS, and radical initiator or photo condition in presence of carbon tetrachloride as in solvent and or heat, which will give the selective bromination of at allylic position. So in 2018 work which appeared in Chemical Communication from German group, where they have used this allylic glycoside in the presence of NBACIBN and tetrachloromethane as in solvent reflux for 30 minutes, it will lead to the formation of this mixed haloester intermediate, and that can be activated in the presence of triflic acid as in promoter, in the presence of dichloromethane as in solvent at minus 40 degrees Celsius to room temperature, lead to the formation of desired oligosaccharide. And at the same donor, same allylic glycoside in this reaction condition can be used in iterative function, which is also known as latent active glycosylation. So in that protocol, what is the scene is there? The allyl glycoside will be first treated with the allylic halogenation condition. It will lead to formation of this mixed haloester intermediate, and then in the presence of acid promoter and acceptor containing latent allyl group, it will be coupled, lead to the formation of disaccharide, and then again this allyl moiety can be transformed to the mixed haloester intermediate, and then again after coupling with the another acceptor containing latent allyl group, it lead to the formation of trisaccharide, and so on. It can go on. So that is the advantage of this method. But still, this method has few challenges. The first is that in situ generated species, the mixed haloester intermediate, which is activated towards glycosylation, that cannot be stored and isolated. That is very much transient intermediate, so that has to be coupled immediately after the generation. And then second problem was that armed benzyl uh, protecting group can't be used in that case. So that brings to the our objective of current work. So we started to explore the possibility of deriving a stable glycosyl donor from an allyl glycoside which can be stored, and it should not be moisture sensitive also, and we are looking towards whether the protecting group manipulation could be performed after the installation of leaving group or not. So for that we started to work on this proposal where it was planned that allyl glycoside first it was transformed to this intermediate mixed haloester intermediate, and then it will be substituted with the thiotolide in the presence of some solvent. It could lead to the formation of either SN2 prime product or SN2 substituted product. The two possibilities were there. So when we started working towards that, it was found that after this allylic bromination step, when it was treated with the sodium thiotolide salt in the presence of dichloromethane as in solvent, with that in the presence of 2 equivalent of this sodium thiotolide salt, the 57% of SN2 prime product has been observed, and there is no trace of SN2 product. And when the mixture of solvent has been used, in that case again SN2 prime product is formed in 45%, and there is no trace of SN2 product yet. But the rest of the product, it is getting hydrolyzed to the corresponding lactol. So when the solvent was changed to diethyl ether completely, and in the presence of sodium thiotolide salt, it gives the quantitative conversion to the SN2 prime product. So finally we found that when this mixed haloester intermediate will be treated with the sodium 1 equivalent of sodium thiotolide salt in the presence of diethyl ether agent solvent for 3 to 4 hours at 0 degree centigrade, it will lead to the formation of SN2 prime product, which contains this vinyl ether, which is a active form of donor, and then thio also will be present there. So once we have this donor in our hand, we started the optimization of this reaction. For that we have taken this managed TCP donor in the presence of this model acceptor 5. It will lead to the formation of this corresponding disaccharide. So for optimization, it was started with acetonitrile as an solvent, and NiS and triflic acid as an promoter at minus 38 degrees centigrade. It gives very low yield of the desired product. So when we switch to the dichloromethane as a solvent, in that case first it was treated with either just treatment of triflic acid or TMSOTF or NiS alone. All these cases did not give the desired product in any amount. So because these are the very common promoter system used in the glycosylation chemistry, that's why these things has been taken, and it is known to activate this similar kind of donor. So when this NiS was used in couple with triflic acid at minus 41 degrees Celsius, it gives some moderate amount of yield. But when triflic acid was changed, substituted with silver triflate, in that case we got decent amount of the desired product at minus 41 degrees centigrade. And when the temperature has been reduced further to minus 78 degrees centigrade, the yield has been reduced. But again, when it was temperature has increased to 0 degrees centigrade, that case we got the maximum amount of yield. So from this optimization, it was found that the NiS and silver triflate as a promoter, when it was treated in dichloromethane as a solvent at 0 degrees centigrade, was the best condition for this donor to be activated and coupled with the acceptor to form the desired glycoside. So once we have optimized condition in hand, we started the synthesis of various oligosaccharides. So we have taken the various mannose, glucose, galactose, pyrenosyl TCP donor. So in all those cases, we have coupled with various aglycosyl and glycosyl acceptor. Like here you will see this is the tertiary alcohol. This is in general it is difficult to couple, but in our case, to our pleasure we have found that 84% of only alpha product we have got. Similarly with the primary acceptor, then secondary glycosyl acceptor, and based on like this is in mannose, then galactose, And then various sugars we have obtained the good amount of yield. Keeping this C4 free OH acceptor of glycosyl donor, which is known to be very less nucleophilic acceptor, this also gives the very good amount of yield. And at last we have done the diglycosylation also, keep taking the corresponding diol acceptor which contain the two free OH group, and when it was coupled with the TCP donor, it gave the very good yield of this trisaccharide in the one step. Once we had synthesized these many glycosides, we went to our second point, whether we can transform the protecting group on the TCP donor. So once we have this TCP donor in hand, the ester-based group were removed using the Gemplane condition, and then further it was protected with the benzyl group, which will lead to the formation of this arm TCP donor. So in case of glycosylation, these arm donors are well known for their very fast reactivity. Once it will be protected with BN group, the reactivity will be enhanced very significantly. So, so once this arm TCP donor was ready, it was found that the previously optimized condition of NiS silver triplet at 0 degree centigrade in the presence of dichloromethane as a solvent, it was again it worked in this case also, and it was found that various aglycosyl and glycosyl acceptor could be coupled, but in these cases selectivity was not very good. In most of the time we are getting the either 1:1, or in few cases where the nucleophilicity of acceptor is less, in that case very less erosion of stereo selectivity has been observed, and we got good amount of selectivity. So if you'll observe the glycosyl acceptor containing the C4 free OH, it gave in those cases we have got the alpha only product. That is the stereoselective glycosylation. Once we have done this, to show the robustness and stability of this TCP donor, we chose to synthesize this GB3 antigen, which is one of the neutral glycolipid and B cell differentiation antigen, and is biologically very important donor to be oligosaccharide to be used. So for towards the synthesis of this GB3 antigen, we started with this galactose TCP donor. It was coupled with this acceptor 35. It led to the formation of disaccharide 17. And in the presence of Gemplane condition, this protecting groups were ester-based protecting group were removed, and selective benzylation led to the formation of this acceptor 36, which contains the hydroxy group at C4 position of this galactose moiety was free, and it was coupled with this arm TCP donor of galactose. And after coupling, we are able to install this alpha 1,4 linkage and then beta 1,4 linkage, and these were the key linkages present in the this GB3 moiety. And that's how it shows that our TCP donor could be utilized to form the stereoselective formation of either alpha or beta linkages. These are the key advantages, and it can be utilized in the formation of various biologically important oligosaccharides. So having done this, we thought to synthesize some really bigger molecules. So we chose to synthesize the branch hexasaccharide, which contains the various alpha 1,6 and 1,3 linkages. So for that, we started with this allyl glycoside donor 38. So first this allyl glycoside, which deliberately in this C6 position and C3 position were protected with acetate group, and rest two were protected with OBZ group. So which will be exploited later. So first this donor 38 was transformed to the TCP donor in the presence of NBSAIB trifluorotoluene reflux condition for 45 minutes to form the mixed shallow ester intermediate, and further after substitution with sodium thiotolide salt in diethyl ether for 3 to 4 hours at 0 degree centigrade lead to the formation of this TCP donor 39. And then this it was coupled with this acceptor 5, which contained the C6 hydroxy group, in the presence of our previously optimized condition, it leads to the formation of this disaccharide 14, very good yield. And then after selective deprotection of this acetate group in the presence of acetyl chloride, in the presence of methanol and dichloromethane 1:1 as a solvent, 2 hours for room temperature, it leads to the formation of this disaccharide 41. And further, taking this donor 42, which contained the only C6 acetate group and rest were the OBJ protected group, and it was undergo double glycosylation to form this tetrasaccharide 43, which contained the acetate group at the terminal position. And again, this acetate group were selectively deprotected in the presence of acetyl chloride and methanol dichloromethane as in solvent system for 2 hours at room temperature, lead to the formation of this tetrasaccharide acceptor. And then again, it was coupled with this managed TCP donor, which contain the OBZ protecting group in the presence of our optimized NIH silver triplet agent promoter and dichloromethane as solvent at 0 degree centigrade to form the desired hexasaccharide in very good yield. So once we have done this, now the next question was that how actually it is getting activated or donor. So to do that, we did one control experiment where this TCP donor has been treated with just NIH in the presence of CDCl3 as a solvent. We did the NMR experiment, and then once we have recorded the NMR, it was found that this carbon which is present one atom next to the thiomoiety. Once after treatment with NIH, it showed the 1 ppm shift. Earlier it was coming at 106 ppm, and then it was shifted to 107 ppm without NIH. And then this CH2 moiety, which is this CH2 moiety, earlier it was coming at 2 diastereomers. Unlike for cis and trans case, we are observing the one is 33, one is 29 ppm. So these were shifted from 29 to 25 and 33 to 29 ppm. And this shows that although this moiety is not living yet, but it is partially getting activated in the presence of iodine. Based on that, we propose the mechanism of activation. In that, first allyl group is transformed to the TCP donor, and when this TCP donor will be treated with NIH, it will form this kind of intermediate where this iodine is getting attached to sulfur, and then after addition of second promoter, which is silver triplet, it will activate it further and lead to the formation of this iodothioalyl intermediate and acrolein intermediate, and because of this side product, it will lead to the formation of desired oxocarbenium ion intermediate, and it can be further coupled in the presence of various glycosyl and aglycosyl acceptor, lead to the formation of new glycosidic bond. And these side products has been characterized using 1H NMR, and this intermediate were observed in GCMS. So once we have this proposed mechanism to show the applicability of our donor, we have used this furanose based glycoside or allyl glycoside. In that case also, we based on our previously optimized condition, we are able to synthesize the furanose TCP donor, and then it was coupled again to the various acceptors in the presence of NIH, silver triplet and dichloromethane agent solvent at 0 degree centigrade. It good, very good to excellent yield of various glycosides. In the case of furanose also, those are the another one biologically important substrate as there. So once we have done this, to show the further applicability of our donor, which is a very key thing in this glycosylation methodology, we have used our donor as an acceptor. So to explore that, what we have done, we have taken this glycosyl bromide as a donor, and we have made the TCP donor as an acceptor like TCP donor, which contains the OH group. So this glycosyl bromide, which was activated orthogonally in the presence of TCP donor, like if you will add silver triplet in the dichloromethane at 0 degree centigrade, it won't disturb this TCP moiety, so it will be coupled with this bromide donor. So once we have this disaccharide in hand, again this orthogonally this TCP donor could be activated and it could be coupled with various acceptor. So it shows that our TCP donor can be used orthogonally either to activate or to keep make it inactive. We can use in the presence of another donors also, which is the very key property. So in conclusion, we have developed this allyl glycoside transform the allyl glycoside to the corresponding TCP donor and which can be coupled with the various acceptor to form the various oligosaccharide in the presence of NIS silver trifluoride as an promoting system at 0 degrees centigrade, and this same system has been used to synthesize the stereoselective one to either beta product, either alpha product, and this will lead to the formation of various biologically important targets. So this work has been published in the beginning of this year in Chemistry European Journal. So this is the graphical abstract for this paper. Thank you.
Nice work and nice presentation, Deepak.
If you enjoyed this session, don't forget to like, share and subscribe. We'll meet you in the next episode, next session. Thanks for watching.